The next speaker is Hugo Morales-Tecotl. Is he ready? Good. Could you make the full screen, maybe?
Is that fine?
If you could make it full screen, it would be more easy to read. But if you have difficulty with it, it's okay.
Is that better?
It's better.
Yeah, that is better.
We leave it there. It's fine. So please go ahead.
Okay. Well, I would like to start by thanking the organizers of this meeting, Jorge and Jorge Alfaro, and as well as Mauro and Carlos Marat. It's very nice to see very close friends through these means. And although it's also very interesting that we can connect this way, on the other hand, today is the first day of teaching at the Metropolitan University, so I will be going back and forth. But anyhow, I will take this opportunity to share some of recent results with you. So this work I will talk about on black holes, on Schwarzschild black hole interior, from the point of view of loop quantization in the approximation of effective dynamics, has been done in collaboration with Juan Carlos Ruelas, who is a PhD student here at WAMI, and Said Rasku, who was a former postdoc here, but now is an assistant professor in Canada. So the outline, the brief outline of this short talk is a bit of motivation. So rather than going through the details for the case of the Schwarzschild interior, I will only point out some details in the case of a free particle, just to have an idea of how do we proceed in this analysis. So I will talk about the loop quantization of a free particle. And then with this idea in mind, I will proceed to discuss the details in the scheme of the interior of the Schwarzschild black hole. And then I will run up with some summary and possible future work. So the motivation here is to understand a bit better the issue of singularities in general relativity, in classical general relativity, from the point of view of one of the proposals of quantum gravity, that is loop quantum gravity. And in this case, in particular, applied to the case of the Schwarzschild black hole. So we will focus on the interior for the reason that is the second part of the motivation, that is classically we know that Schwarzschild black hole is the interior. Schwarzschild black hole is or can be represented as a Katowski-Sachs model. So that makes it amenable for the procedure previously used in loop quantum cosmology, that is spatially homogeneous models. Other motivations that come along are also related to the issue of how to describe without analyzing in full detail the quantum models, even though these are symmetric models, more simplified, a bit simplified. Still, it's a bit problematic. Sometimes one has to use numerical approximations, but it's also useful to use some kind of quantum effective models, and I will give a brief description of what do we mean for that. And a piece of technical stuff is that in order to establish these models, one needs to introduce some auxiliary structures. However, the physical results should be independent of these auxiliary structures. So it's important, and that's a key issue that has been dealt with in recent years. And finally, precisely the main part of the talk is what is the effect of the inclusion of inverse triads. They have been usually neglected, mostly for reasons of simplification, and alluding or trying to argue that their effect is rather small or negligible in comparison with the other contributions. However, it is not always the case, and so we will see what happens in this interior of the Schwarzschild black hole. So what do we mean by the loop quantization of the free particle? So this is a different approach to define a model that is actually quantized on a lattice. So the one possible point of departure is to consider what we call the polymeric Hilbert space, that is defined considering the real line. This is a particle in one dimension. Consider the real line with a discrete topology. So this Hilbert space is actually one of functions which are square summable, and one can introduce to define this Hilbert space, this polymeric Hilbert space, inner product for every point in this real line, possessing this property that is substituting the usual delta Dirac delta by a Kronecker delta. And because of this discreteness, the Stone-von-Neumann in this Hilbert space does not apply as usual because of this structure, discrete structure. Hence, there is no generator of spatial translation, and it is not possible then to express the translations with a scale mu, say, as the exponential of such generator. However, that doesn't forbid to proceed with model, and that's what one does here. And it's possible to establish this Weyl algebra, that is the finite translation with the position operator yielding this commutator. And within this discrete representation, it is possible to make it consistent. To introduce a Hamiltonian for the case of the free particle, since there is no generator of translation, namely in this Ringer quantization, the usual one, we have the p squared over 2m. Here we don't. Instead, we have to use or propose to use a substitute in terms of the basic objects of the model, and the Hilbert space actually can be represented as a direct sum of Hilbert spaces, all for regular lattices, but it's a continuum of Hilbert spaces. Namely, we have this. This should be x naught. That is the base point of a lattice between 0 and mu, the step of the lattice, and this is a non-separable Hilbert space, in fact. But to proceed, we will consider a super-selected Hilbert space, only one of these, and in particular, we will assume we're working with the lattice center at the origin, so x naught would be 0. Of course, we can use here the completest relation associated with the position representation, in which here L, in this case, L is an integer, and mu is the step of the lattice. So we have this completeness relation for the position, and in the case of the momentum representation, we have this. Here, momentum representation, remember, there is no p operator, no generator of translation. However, what we call momentum representation is just the basis in which this operator, this unitary operator, is diagonal, and p is bounded below and above. To proceed, one can solve the eigenvalue problem, say, for the particle in this Hamiltonian approach, in this discrete approach. And as we know, this is one way to see a null problem. You probably recognize the spectrum here is given by this structure in which p is bounded. And only for this case, for this approximation, we recover the usual case. The specific wave functions, eigenfunctions in coordinate representation or in momentum representation, are just the kind of plane waves, except that these are discrete. And in the case of the momentum representation, we have the Dirac delta. This is a Dirac delta. One can calculate, say, the propagator and one obtains this nice result in which xj and xr are two discrete positions of the lattice, and the corresponding dependence is through this Bessel function, capital J. And notice the order of the Bessel function depends on precisely the integers that are related to this position xj and xr. And it fulfills the usual properties for the propagator, say. Another very convenient way to represent the propagator for this mechanical model in the lattice is precisely the path integral representation, in which one gets, instead of the standard classical action, a modified action which we call the effective action. And indeed, this one can, under certain approximation, one can describe the quantum model by using this effective action whenever this approximation is valid, of the kind WKB, say, but in this case for the effective action. And of course, the action is, this effective action is modified. The effective dynamics is different from the classical one, and it has within it the scale that we introduced at the beginning, this scale mu, this length scale. So that's basically the idea of this effective dynamics that one can use within this quantization by using this path integral approach also. So let's go now to the case of the interior of the Schwarzschild black hole. So classically, we have, as we know, this is the solution of the vacuum Einstein equations, and we have the standard structure. And in the interior of the for the black hole, we have this other structure, in which basically, because of the switch of the Killing vectors, the radial and the time, they interchange their roles. And one can see very easily that this structure, the interior classical solution, is just part of the so-called Kantowski-Sachs models. And so that's what we, or what people propose to take into consideration in order to quantize this model. Using the so-called Ashtekar variables, in which we have an SU2 connection and a densitized triad, this capital E have a square that essentially is a trimetric, and they are integrated in the general case for full general relativity, where they are integrated. And in this case, because of we have an anisotropic but homogeneous model, to make sense of this symplectic structure, we have to integrate over an interval, and that interval is what naturally introduces an auxiliary quantity, that is the size of the radial direction, say, in the interior. And we have to consider this scale, and since the topology of the spatial interior has, in particular, an S2, this is the scale of this S2, this R0. So there are two auxiliary quantities. In the prescription that we will consider later on, R0 is actually will be taken as the classical Schwarzschild radius. It is convenient to make some redefinition by introducing these scales, so that we end up with two pair of canonical variables, CPC and BPPV, essentially. In terms of these last variables, it is possible to rewrite the metric as having this structure, and this is what we call the lapse function. And in order to proceed and consider what we want to study in this work, we have to remember that the general relativity is a constraint theory because of the symmetries it possesses, and in particular there is the Hamiltonian constraint, which in terms of these Ashtek-Arbor variables takes this form. And these are the precise structure of the terms, what we call the inverse triad contribution. Here, there is two curvatures. One is associated with this connection A of the Ashtek-Arbor variables. And this omega is essentially a curvature calculated with extrinsic curvature defined in terms of the spin connection associated with this densitized triad and the Ashtek-Arbor variable A. To proceed with the quantization, one introduced with this.
Can I just break in? So you've been speaking for 15 minutes now, I'm just telling you.
Okay, thank you. Then, well, one proceeds just to introduce the loop holonomy variables. And with these essentially exponentials of the degrees of freedom we have introduced that are related to this anisotropic model, we have this kind of shift operator that we had like in the particle model, the free particle, and the other operators are just diagonal. So that's what makes useful the previous discussion on the particle. It is possible to obtain this extraction amplitude. That is, the name comes from the fact that we actually have a constraint system, so we have to take this aberration procedure. And finally, the effective constraint takes this form, which contains these functions beta 1 and beta 2 in red, which are related to the inverse triad corrections. And you can see, or it is possible to check very easily that in the limit in which the arguments here are small, one recuperates an action which is the classical action, but written in terms of these variables PB, PC, C, and B. The behavior of these functions is associated to the inverse triad corrections is that after some critical value, they tend to 1, but they have modifications for smaller than PB0, say, values. They have problems because they are not invariant on the rescalings, and then they have potential risk of being unphysical. But there are other options, so that's what we discuss in our paper, and I will not give the details here. One of the outcomes of this analysis that is has been discussed by Ashtek and collaborators is that instead of having, in particular, singular black holes, what we have is a transition between black and white holes, and it can be shown explicitly that actually the curvature remain finite in the would-be classical singularity. So in conclusion, there are inverse triad corrections to the description in the gravitational constraint usually are neglected, but they are dangerous in the sense that they may lead to the introduction of all the dependence on auxiliary structures, but there are possible ways to eliminate and correct that notion. In the future, well, it is possible to analyze the validity of this effective theory. This has been done for the case of loop quantum cosmology, but not in the case of the black holes. And there are some possibilities to actually deal with the more complicated case, the full quantum description of the interior of the black hole, not in terms of the effective dynamics. And also, there are some attempts to consider also the exterior, but that still needs some further work. Thank you very much.
Thank you. And before we take questions, I just want to announce something. That will be a conference picture taken today, and that'll be at the end of this session, which is then after Gamonal's talk. So in about 40 minutes, I guess. And I see there is a question from Luca Smaldone.
Yes, thank you.
Yes,
Just a technical curiosity. At the beginning, you talked about these polymer Hilbert spaces, and you talked about violation of Stone von Neumann theorem. Is this violation due to non-trivial topology? So the fact that you cannot construct GNS construction continuous measure for a projector?
Yeah, well, it may be related to that, but it can also be seen from the more simplified point of view. And given the structure of the bases here, one can see that the condition for the Storm von Neumann on continuity of the action of the operators does not hold. So you lose this continuity requirement.
Yeah, okay, so it should be, because there are, my knowledge, two ways of avoiding Storm von Neumann, you know, infinite number of degrees of freedom and non-trivial configuration space topology, I think, which leads to this discreteness, I think, is the second one.
Yeah, just to enrich the question, I understand there is the possibility to have a generalization of the Storm von Neumann theorem for this kind of spaces. Yeah, but it's another version.
I see. Very interesting. Thank you.
Thank you.
Okay, thanks. I don't see any other questions, so thanks to Hugo again for his talk. Thank you.
Thank you very much.
Sorry, was there another question?
Yeah, I wanted to ask something brief.
Yeah, please, Jorge, go ahead.
The thing is that I remember in this matching of the interior and exterior black hole in the Ashtekar approach, it is not possible to have a asymptotically Minkowskian space, right? You cannot reach the Minkowskian space. You get the contribution there.
Yes, there are actually a couple of words regarding this picture I have here. There are two, discrepancies from different authors, precisely underlining that. So this requires further studies.
Okay, thank you.